Hello, my name is Alex Ludwig, and this is my EE452 final project for the spring 2022 semester. I chose a microphone-controlled RGB LED board. Brief overview, this project was to fulfill the requirement of designing and developing an embedded system using techniques we learned in class. I selected RGB LEDs due to their popularity and functionality, and I wanted to control them using a microphone. So the first step was to identify and analyze the system. Light displays, in my opinion, enhance the user's listening experience. There's many of these devices on the market right now, ranging from complex to simple, and they consist of a microphone, a microcontroller, LEDs, and a power supply. And I used this logic flow to represent the requirements necessary. There needs to be a sound source that needs to be acquired by a microphone to produce a signal, which goes into an analog to digital converter. And then there needs to be some sort of design environment to allow you to program these results to be outputted to, the RGB LED strips, and in this project, an LCD screen. So the input is acoustic waves generated by the music, and I use the SparkFun sound detector to acquire this analog signal, and this required a 5-volt DC power supply, a ground, and the envelope pin is where the data gets sent to. And for the output, I use the WS2812B RGB individual addressable LED strip. This also required a 5-volt DC supply, a ground, and a data signal, as well as the LCD 1602 module that we used in class. So the sensors, the amplitude of sound is measured by the sound detector. This analog value is sent to the microcontroller from the envelope pin. The loudness of the sound desired that dictates the range that you need to set the sound detector to. And this is programmed in the code, because if the range is not appropriately set, the mic will not detect sound, or it will always be detecting sound. So the signal conditioning required, the incoming sound waves hit the diaphragm of the mic, causing a mechanical deflection. This is in the form of current because the coil moves through the permanent magnet, and this current is the analog signal sent to the analog to digital converter. And it needs to be a digital signal so the microcontroller can use it. The controller tasks required for this system needs that analog to digital converter. It needs to supply power to the system. It needs to also send a pulse width modulation signal for the LEDs to operate. And then you need an integrated development environment. So the hardware controller selected was the Arduino Mega 2560, and this is available from the Embedded Systems Lab. There's large amounts of educational resources available, and it's capable of performing all of the control tasks. So here is a demo. I also have one going in the back here of the FAST library, FAST LED library that I utilized for these to control the RGB LEDs, and it was written in the Arduino IDE. This was the demo reel 100 playing in the background here. They also had Pacifica and Twinkle Fox. But the parameters that needed to be set within this library code were the output data pin, the LED strip type, the color order, which was RGB, the number of LEDs, which I had here was runs of 20, the brightness, and the frames per second. And then to utilize the microphone, I used code from GitHub, the sound reactive LED strip developed by Rupak. And I also used the liquid crystal library for the LCD screen. Here was the first of the testing. I ran it with 150 LEDs, and you can see the flicker. It's not really performing the way I wanted it to. This was because each RGB LED draws 60 milliamps at full brightness, and this was connected to the Arduino, which can only handle 200 milliamps. So I purchased a power supply that can handle 10 amps of power at 5 volts. Also, the data signal, the voltage drops when these LEDs are in series, so I had to remedy this by creating this board, 8 runs of 20 LEDs, and adding a 20 ohm resistor. So this is a picture of the prototype from left to right. We have the Arduino, the LCD screen, the mic, the board itself, and the power supply. This shows the LCD with an input signal of 30. This is what's reflected on the LEDs. It's the magnitude that they're going to light up to. Finally, the prototype. This is when it's at full sound value, and it's reflected instantaneously as different colors across the strips and lighting them all up. And this is, at max volume. I'm going to play a quick video here to show it reacting to a sound. So in conclusion, this microphone-controlled RGB LED board clearly demonstrates the design of an embedded system. Controlling the RGB LEDs using music, clearly displayed. I'd like to expand upon this by maybe adding more runs of LEDs and increasing the run length, and then maybe controlling each run with an individual data pin. And then, I'd like to build a case and improve the overall hardware appearance. Here are some citations and any questions or comments, and I'll run a demo here of it working. So when you see me talk here, it will light up the signal, and the LEDs will increase based on the amplitude of sound I'm making and based on the sensitivity the mic is sent to. Pretty cool, huh? Thank you.